This is the part 2 video for the Introduction to Integration and the Antiderivative. Let's continue our discussion with working with a second derivative that's just a little bit differently than the ones that were on the previous video. And I think you'll see pretty quickly why it's different. Now this one looks fairly simple. X is to the power of a -2. Now you know you're going to integrate twice or take the antiderivative twice. And so it looks like we're going to go through that x to the -1, which could yield the natural log of x. That's not different. Okay, so can you look at the information that's given to you and see how it's different than what we've seen in the previous video? Okay, have you got it? In the first video, the previous video, we typically had information given about the first derivative because remember we go from the second derivative to the first and they gave us some information about the first derivative so we could find C. And then we did the antiderivative again and went to the original function and they gave us some information about the original function so we could find D. Okay, now this case they just gave us two pieces of information about the original function. So let's pretend for just a second that you're on the test or some assessment. And this is really important. It's like 50 points out of the assessment or out of the quiz or the test or whatever. And you're looking at this going, I have no earthly. So let's get started because blank, if you leave it blank, it's definitely wrong. Okay, so let's go, well, let's do what I can do. I'll figure it out when I get there. So to back it up to the first derivative, right? I add 1 to the power, divide by the new power, and add c, correct? So the first derivative is minus x to the -1 plus c. And you go, well, I don't have any information to apply at this point, so let's just keep on going. Now again, when you do some sort of antiderivative, you can always mentally or on another piece of paper take the derivative of it and see if you get back to where you started so that you can check yourself as you go. Because any points that you can save on any sort of major assessments are points that you might need when you get down to the final. So save yourself some points by checking yourself. So let's look at backing this up just a little bit more. Now remember, if you forget this pattern where x to the -1 or 1 over x is going to result in a natural log of x when you take the antiderivative. If you just keep doing what you're supposed to do, if you remember the pattern and you add 1 to the power and divide by the new power, what am I going to do with 0 in the denominator? That's going to alert you that, oh, that's right, I was supposed to notice that this is going to be a natural log. So this is going to be the negative of the natural log of x. And usually, they have the absolute value of the natural log of x, but they told us x was going to be greater than 0 anyway. Because you remember that the natural log of x looks something like this. That's its graph. And it doesn't get to cross at x is equal to 0 asymptote. Okay, so that's the natural log of x. We had a constant c, so now it must have the variable x, and then we have a new variable. Now, all right, so this is my best guess. Let's still think of ourselves as being on the test. I've gotten up to my original function. I've done everything I know how to do with taking the antiderivative. I'm not really comfortable with the fact that I didn't have a first derivative piece of information for C, but let's just keep looking at this for a second. They did give me two pieces of information about this original function, and I have two variables. So if I have two pieces of information and two variables I'm trying to figure out, this could probably work out, right? Now that we have this function, the original function, and we have this natural negative natural log of x plus cx plus d, then what we can do is to say, well, I've gotten as far as I can get with the approach of trying to do the antiderivative twice. I need to try to apply these. So we're going to try to apply this information into here because they did give me two pieces of information about the original function. I have two variables in the original function. Let's see if we can work that out. So if I'm going to apply the fact that they told me f of 1 is equal to 0, then x is 1, y is 0, so 0 equals the negative natural log of 1 plus c times 1 plus d. So we'd have the natural log of 1 equals c plus d. Now, you may be really comfortable with this and you may not be remembering this very clearly, but the natural log of 1 is actually 0. This has to do with when we were working with logarithms back, maybe the last time you saw it was in algebra. Okay, so pre-calculus, something like that. So I'm going to attach a linked video, and the link will be down in the description. I'm going to attach a linked video that just has a very quick reminder of how this works and why it's equal to 0. So this is 0. And let's call this equation 1. And then we're going to apply the fact that they told us that for the original function, when x is 2, y is 0, so 0 equals the negative natural log of 2 plus c times 2 plus d. So we would have the natural log of 2 equals 2c plus d. Now, there's not any nice, clean integer values for the natural log of 2, and so we're going to leave that this way. Now look at this, and you see how I have two equations and I have two unknowns. I have a c and I have a d. So this should be kind of triggering a little bell in there for pre-calculus and algebra where you could either use the elimination method and get opposite c's or opposite d's and then line them up and then add down and eliminate a variable, or the substitution method. And I'm going to use the substitution method, and I'm going to solve equation 1 for d. So d would be equal to a negative c. And then I'm going to substitute it into 2. All right, so I'd have the natural log of 2 equals 2c, but d is a negative c, right? This d is a negative c from this d. All right, now I have one equation and one unknown, so the natural log of 2 and 2c minus a c is c. So I know c is the natural log of 2. Okay, and then I could substitute it into this, back into here. Now d is equal to the negative c, or you can go all the way back up into here. D plus c is 0, one of these two. And if c is the natural log of 2, then d is the negative natural log of 2. So here we go. Remember, we had f of x was equal to the negative natural log of x plus cx plus d. And now we know that it's negative natural log of x. Remember, we said x had to be greater than 0, plus c, which is the natural log of 2, times x, minus d, which is the natural log of 2. So this was cx and this was d. You get? So this would be our answer. So if they don't tell you one evaluation of the first derivative and then another of the second derivative, then what you have to do is get it all the way to what you need to the original function and then work them together at that time. Makes it a little harder. It's usually a little easier if you have a piece of information about an intermediate result so you can find C first and then find D. Now let's go ahead and try an application of how this works. And remember that when we worked with taking the derivatives, if you have a position function, the derivative of position is velocity, and the derivative of velocity is acceleration. So let's try this problem here where we're going to be working through accelerations and velocities. And here we have a problem. Water balloon is dropped from the roof of an apartment building and falls 130 feet to the ground. Find an equation that represents the distance the water balloon is above the ground at time t. How long does it take for the water balloon to strike the ground? And if you throw the water balloon with a downward velocity of 10 feet per second, how long does it take to reach the ground? Okay, so this should be a how long. All right, now let's talk about this for just a second. When you are going through this problem, we kind of need to get our head wrapped around the problem per se. So what's the difference between the initial statement and part C? Well, let's see. On part C, it says that you're going to throw the water balloon downward. And on the original statement, it just says it's dropped. So on the original statement, you have to imagine that you're standing there with this water balloon and you just let it go. Okay, so the original statement is we're just going to let it go. We're not going to lob it up and then let it fall or throw it down and let it continue falling. We're just going to release it. Okay, that's one of the things that we need to be aware of. The other thing is that you notice on part A, it says find an equation that represents the distance or the position. So if I have something that says it's being dropped, the only thing that actually makes things fall to the ground is gravity, right? And in the English system, what you would have is this 32.2 feet per second squared is going to be acting downward. So what we're going to have to do is to work from acceleration up to position, which means I'm going to have to do the antiderivative twice. It also means that you're going to have to remember what gravity is. Okay, the effect of gravity, acceleration due to gravity. Right. So let's get started. And what we know is that the acceleration due to gravity, since this is all I'm doing, is just letting it go, and gravity takes over. This is my general equation. Right? Then we're going to do the antiderivative, and when we do that, we're going to back up to the velocity. So you would do the same thing you always do. Now this is in terms of t as opposed to x, but we can do this, right? And we would have negative 32.2, and if it's a constant now, we must have had a t before, and then we have some unknown constant. So we're going to have to deal with the fact that we are standing up here on top of, not drawn to scale by any means, on top of a roof line of an apartment. We have our little balloon. We're going to drop it down here. In order to come up with some of these constants, like since we're going to take the antiderivative twice, we would need two pieces of information. Can you think of something that would be appropriate? Because in this case, they're not telling you what the two pieces of information are. You're supposed to sort of figure it out. Okay, so pretend this is you up here being crazy. You're not trying to hit anybody in particular with the water balloon. You're just going to drop it off and see what happens. Okay, so when you drop it off, what would be the velocity? Because look at this equation right there. It would be really nice if I knew something about the velocity. So when you drop it, the instant you drop it. So when time is equal to 0 and you're just getting ready to let go, isn't the velocity 0? Make sense? Okay, so I'm going to apply the fact that at the instant I let go, the velocity at time 0 is 0 feet per second, right? So 0 is equal to minus 32.2 times 0 plus c. So c is equal to 0. So my velocity is minus 32.2 t. And that's it for that part, right? Now, what they want to know is actually what the position function would look like. So I'm going to do the antiderivative again. So s, which is the position, or the distance in this case, you would have your minus 32.2 t. You would add 1 to the power, divide by the new power. Okay, plus we already used c, so we're going to have d. So it would be really nice if we had some sort of information about the position. So do we have any information up here that talks about the position when maybe we get started? Well, when we get started, the distance from here to here is 130 feet. So we knew that the velocity when we started was 0, and we know that the position is 130 feet. Right? When I first get started, the balloon is 130 feet above the ground. So 130, okay, well, let's write this out. So we're going to apply the fact that S of 0 is 130 feet. So 130 equals minus 16.1 t squared, but t is 0, plus d. So d is 130. So S of t is negative 16.1 t squared plus 130. And this is the answer to part A. Right? Then part B says, how long does it take for the water balloon to strike the ground? Now, if the water balloon is going to strike the ground, because the answer is to ask for t, right? So it's asking you to find t if it hits the ground. Well, when you hit the ground, if up here is 130, down here is 0. So the question becomes, when is negative 16.1 t squared plus 130, when is that equal to 0? So you would have t squared is 130 over 16.1. So t is plus or minus the square root of 130 over 16.1. And when you run this on your calculator, you get plus or minus 2.84157. So we'd only want positive time because we can't have negative time. So 2.84 seconds. Okay. Now, what does that mean to you as the person who just dropped the water balloon? Well, what that may mean, depending on what's going on, is that gives you 2.84 seconds to duck back in case somebody saw you do that and you don't want to get in trouble. All right. Now, if you didn't aim at somebody and you didn't get anybody wet, they may just be kind of like put out. Okay. So try not to hit anybody if you do this. All right. Now, so the next question was, I'm not promoting you throwing water balloons off the top of buildings. I'm just saying, if you do, all right, that's how long you have to duck back. But try not to hit anybody because that's not nice, right? So students are always trying to do odd things and with me, because I guess because I laugh a lot. Anyway, so one time they actually tried to aim So we built a trebuchet. So they were actually trying to get me with a trebuchet and water balloons. But, please don't try to aim at anybody. All right, now here we go. So the next question says, what if I don't just drop it? Okay, what if I have a downward velocity of 10 feet per second? So I'm not just going to be standing there with this water balloon and go, let go. I'm going to throw it down. Okay, what would that do to the final result for how long it's going to take to hit the ground? So if you throw it down, do you think it's going to take less time to get to the ground? So you would have even less than 2.84 seconds to pull back. Right, let's see. But it's kind of like the same pattern, right? So you would start off and you would have your acceleration is minus 32.2 feet per second squared, right? And we're going to do an antiderivative. So the velocity would be negative 32.2 times t plus c. But in this case, right, the velocity at time 0 is not 0. It's actually a negative 10 feet per second. Now, can you see why it's negative? If you're measuring up is positive for the distance, 130 feet up was positive 130 feet, and you are throwing this down in the opposite direction of measuring up. So if up is positive, down is negative, it's going down the same direction that the gravity is. So it's going to be a negative velocity. If you don't remember your signs, then it's going to affect your final answer and then you would be wrong. So let's apply this v sub 0 equals negative 10. And you would have negative 10 equals negative 32.2 times 0 plus c. So in this case, c turns out to be negative 10. So v sub t is equal to negative 32.2 t, and c is negative 10. All right. So can you compare? So this is the velocity when I don't throw it up or throw it down. Okay, I'm just letting it go. This is the velocity with my extra component where I'm combining a downward velocity with the effect that gravity has. All right, so now we're going to take the antiderivative again. So it's negative 32.2. You would add 1 to the power, divide by the new power, minus 10. If it's a constant now, it used to be a negative 10t, and you'd have a d. So s is negative 16.1 t squared minus 10t plus d. Now, this is kind of familiar. If you've had physics in your past or something like that, do you remember that negative 1/2 a sub c t squared plus v sub 0t plus s, right? It looks kind of like that, doesn't it? All right, now what we're going to apply is, even though we gave it an initial nudge, okay, originally we're still standing up there at that 130 feet up above the ground, right? That would be my initial condition. So 130 equals negative 16t squared minus 10t plus d, but all the t's are zeros, right? Because t is 0. So d is 130. So s of t is negative 16.1 t squared minus 10t plus 130. And then the question is, when does it hit the ground? And it hits the ground when s is 0. But this one's not as simple to solve as the other one. This is going to require us to do the quadratic formula. It doesn't factor. Okay, so t would be, and remember the quadratic formula? Let me write it over here. Negative b plus or minus the square root of b squared minus 4ac over 2a. Remember that? So it's negative. What's b? Negative 10. Remember, this is a, this is b, this is c. So plus or minus the square root of b squared minus 4 times a times c. All of it over 2 times a. Okay? So cleaning this up a little at a time, you have 10 plus or minus the square root of 8472 over negative 32.2. So this would be 10 plus the square root of 8472 over negative 32.2, or 10 minus the square root of 8472 over negative 32.2. Now, if you can tell, 10 is definitely positive, plus the square root of 8472 is going to be positive, divided by negative is going to give you negative, and it turns out to be something like negative 3.1691. But you actually don't have to do this because this gives you negative time. And we don't do time travel backwards, okay? So we can't have negative time. This one, though, depending on the size of this square root, and it looks like it's going to be pretty big, is 10 minus, give or take, 92.0435 over negative 32.2. So this is going to be a negative divided by a negative. That would work. So this turns out to be 2.5479. So t is 2.55 seconds. Now, in case it's been a minute, so it's 2.55 seconds if you throw it downward, compared to 2.84 seconds if you just release it. All right, and that little 0.3 of a second might be kind of important. Okay, so there's an application. In the description will be some problems for you to practice, and there will be a link to a little bit about the natural log, just a very brief reminder, and then a link to the next video. So here we go. Integration will be coming up soon, and Riemann sums and all sorts of wonderful things you may have heard about. And I will see you at the next video.